Hello and welcome to part 16 of the Minimapper series. Today I'm going to talk about the Link-434 communications device that I'm developing. Just going to talk about the schematic side of it today. Just to recap, this is a thing, it's a 434 megahertz thing that will, on one side, plug into a USB port on a PC, and on the other side will connect to the Minimapper, and the two sides will be able to talk to each other. For a thing that only has two ICs on it, a microcontroller and the 434 megahertz transceiver, this turned out to be an awful lot of work because it's all very new for me. It's a microcontroller I've not used before. I've not done any RF stuff before, so I'm kind of winging it slightly. I'll talk through the schematic a little bit. There are a couple of vaguely interesting things with it, so let's get to that. So here's the top page of the schematic. You've got the microcontroller here. It's a Silicon Labs EFM8 UB3, and we've got the 434 megahertz transceiver here, which is on a separate sheet we'll look at in a minute because we've got lots of passives that go with it. So the idea with this thing is that you can use it in two modes. You can connect this thing to a PC using a USB connector. So there's a USB plug, which is basically just a card edge connector. So there are four PCB traces that go to the edge of the board, one each for the power and ground, and one each for the two sides of the differential pair that carries the USB data. And so the idea is that you can plug this thing into the USB port and just shove the edge of the board into the USB port on your PC, and it can talk to it. And there's the usual things that you get when you do a USB connection. There's some ESD protection diodes. There's a ferrite bead for filtering the power from the USB bus. And this voltage divider here is just something that the microcontroller uses for detecting the presence of a USB connection. And the USB data pins, D plus and D minus, go directly to dedicated pins on the microcontroller. And so that's one way of using this thing. The other way of using it is not connecting a USB connection to it, but using this header, which will be used when you connect the thing to the Minimapper. And then the Minimapper and the Link-434 communicate using a UART, and the power for the microcontroller and the transceiver comes from the Minimapper. So there's a 3.3 volt power connection from the Minimapper. So there's when you do this, these two different power modes with the microcontroller, you have to do a bit of stuff. So when you power this thing from the USB, you connect the USB power to this VREG in pin, and the microcontroller has an internal regulator, 5 volt to 3.3 volt regulator, that then drives VDD as a 3.3 volt output. So you can use that to power everything else. When you're not running the thing off of USB power, and you want to power it directly with a 3.3 volt power input on the VDD pin, you have to tie these two pins together and that lets the microcontroller know it should switch off its internal regulator. And so I spent a while thinking about various fancy ideal diode type ways of doing this, but I ended up just putting a little jumper on here to tie these things together. So when you're running it in USB powered mode, you leave this open. When you're running it powered directly from VDD, you install a jumper here, and that makes everything work. There are almost certainly better ways of doing this, but I couldn't quite figure out how to do it. The other things connected to the microcontroller are a couple of indicator LEDs and a switch, which can normally be used as a general purpose I/O switch, but it has one little wrinkle, which is that it's connected to this P2.0 signal. And this gives you a fail-safe way to get into the bootloader that's factory installed on these microcontrollers. So there are three ways to get into the bootloader. One is the first time you power up the microcontroller, and so the program flash is not initialized at all. It'll go into the bootloader. The other way is a software way. So you can trigger a software reset with setting up a couple of other things, and the bootloader will start. And the third way is to pull this pin low during a power on reset. And what that means that installing this switch here gives you a fail-safe way to get into the bootloader. If you program some software on here that doesn't do the software reset bootloader thing properly, then that doesn't mean that you've bricked the thing completely, because you can hold down this switch, plug the thing into the USB port, and the bootloader will start, and you can reprogram the thing. And so I'd been thinking about just using this USB bootloader for programming this. There is this C2 programming and debug interface as well, and I'm undecided about whether to bring that out to a header. There are also a few other GPIO pins that could be brought out, and I've got some other ideas for how to use this thing. So I'm thinking that I might extend the headers a little bit to make use of that. Anyway, the other signals that come out of the microcontroller all go to the transceiver. So you've got a bidirectional data signal. So this is a logic level signal. You've got a thing for enabling the transceiver, and you've got a thing for switching between transmit and receive mode. Coming the other way, there's an analog signal that has the receive signal strength indicator from the transceiver, and that'll go to an ADC on here and be able to sample it. The other three pins here are a 3-wire serial connection for configuring the transceiver. And I misread the datasheet originally. Originally, I thought this was a normal I2C SM bus kind of interface, but it turns out it's not. It's a custom serial interface, so I'll have to write some stuff on here to basically bit bang this thing on here. And that's a little bit annoying, but it's kind of neither here nor there. Just have to do it. So that's the microcontroller side. On the transceiver side, you see there's lots of passive stuff all around here, and basically all of this is taken pretty much directly from the MAX 7032 datasheet. So let's just quickly pull that up. So the MAX 7032 is this transceiver that it comes as a kind of toolbox where all the different bits of your transceiver, the connections between them are available as pins on this package. And the way you wire them up is fairly complicated, but there's an application circuit in here, and I've basically copied this. I've worked through everything in the datasheet, and I have a relatively good understanding of how it works, but it's fairly complicated, as you can see. One thing to say is that, as often with these things, the transmit side is super simple and the receive side isn't. The transmit side here is there's a PLL to generate the signal that goes to the power amplifier, and then the data signal is basically just used to switch the power amplifier output on and off, because this is amplitude shift keying or on-off keying. All the rest of the stuff in here is to do with the receive side of things. So it's significantly more complicated. And so you've got a low noise amplifier, you've got some mixers, you've got some intermediate frequency amplifiers, and then you've got a kind of data splitter, data discriminator thing going on here. And basically almost all of the passives on here are to do with that stuff. So there's a crystal here for setting the 434 megahertz frequency that the thing uses for transmit and receive. The PLLs inside multiply this up by, I think it's like 24 to give you the 434 megahertz. There's this antenna matching network here, which I don't really understand. For the antenna, I'm just using an SMA connector, so I can put a whip antenna or just a bit of wire on there. But this matching network, when you're transmitting, the output signal from the power amplifier comes out here. When you're receiving, the received signal comes to the low noise amplifier here. And this path is switched on and off between transmit and receive by this signal. And then basically all of this other stuff down here is the receive chain. There's a tuned circuit here, which is tuned to 434 megahertz, which is used to filter the input as to the kind of receive side. There's a discrete crystal filter here, which is the intermediate frequency filter. It's a 10.7 megahertz crystal filter. So the output, the signal comes into the low noise amplifier here, comes out of the low noise amplifier here, goes into the mixer here, comes out of the mixer here, goes into the intermediate frequency amplifier here, and then all of the rest of this stuff is to do with this data discrimination problem. So this is basically deciding when the power received in the intermediate frequency band is enough to say it's a logic level 1, or it's not enough and it's a logic level 0. And all of these passive components here are set according to, basically they determine timescales for various things in this data discriminator. And it's fairly complicated, and I don't understand quite a lot of the details. I'm hoping to become more familiar with them as time goes on, but I'm not going to get into it now. Yeah, so that's basically it with the schematic for this. Like I said, I might make some changes to do with bringing more microcontroller signals out through headers, because I've got some other ideas for things I could do with this. The next thing I'm going to do with this is layout, obviously, and that's going to be quite interesting, because the microcontroller and the transceiver come in small QFN packages. One's 5 by 5 millimeters, one's 4 by 4 millimeters, and they're smaller than anything I've worked with before. And what that means is that I may also end up using smaller passives than I've used before. I normally use 0805 resistors and capacitors, because they're relatively easy to hand solder. But if you put all those passives that go with the transceiver in as 0805s, they slightly overwhelm the transceiver, and it's a little bit difficult to lay them out. So I'm probably going to end up using 0402 passives. And that's only possible because I've been doing some experiments with reflow soldering, using a very kind of homegrown approach with a little hot plate and a hot out pencil. And that works pretty well. So I'll probably end up doing that. The software side of this, I've got some interesting ideas for testing and simulation that should make that fun. So I'm going to be getting to that. The next video I'm probably going to do is going to be going back to the motor prototype board, though, because I've assembled that, making good progress with the software, and I want to get around to testing it, actually making some wheel spin. So see you next time for that.